We are presenting now linear transformations from Rn to Rm. So we are dealing with finite dimensional spaces. In that case, we will also call those linear transformations that go from Rn to Rm matrix transformation. You will see how we build the standard matrix for those transformations, linear transformations. And at the end we will compose 2 or 3 or more of these linear transformations and see how to find the standard matrix for them, for the composition. So first, couple of reminders of the definition of the transformation. So transformation is a function or a mapping that transforms objects that live in a linear space V, so it assigns to each one of them an image, an element in a linear space W. And this is typical notation. T is transformation from V to W. Now when V and W are the same space, there's another name we give it, it's linear, it is an operator, but that's just a detail, it's not so important. What matters is to realize that we have a domain V, and then T is taking objects from the domain V and transforming those objects somehow, following some rule, into objects of the codomain W. So each X from V is transformed and we create an image of X, which is called Tx, and then the set of all those images is called the range of the transformation. So range is a subset of W. Those are the images of the objects in V. So this is an illustration. So again we have transformation T, it's a function, maybe of several variables, or it takes different objects like polynomials or matrices. It doesn't need to be just numbers and vectors. So it takes objects from V and it transforms them into objects that live in W. So TV is an image. So we have a domain, T is taking people from the domain to the codomain, but more particularly it is taking them to the range. Range is subset of the codomain. Sometimes for some applications it's going to be the entire codomain, it depends, we will see. So that will be interesting to see what is the range of a transformation. Okay, so again domain, and then the transformation transforms things into objects of codomain, and what we have as a set of images, it's called a range of the transformation. So obviously if we have a range, we have a null space also. So a range space and null space, a general term would be also kernel of a transformation. So these are just words, new vocabulary. So the range is set of images of objects from V. So you take an object from V, you apply T to that object, you get an image. Image lives in the codomain. So set of all images is called range. And then null space of a transformation or kernel of a transformation will be set of all vectors in V that are sent or mapped to the object 0 or vector 0 living in W. So you take people from V and we see what are the objects V that transformation sends to 0. So that's the kernel. That's a classic definition. So all the objects whose image is 0. So that's a kernel. So those are people that live in V. So for instance, if I have 0 transformation, in this case, the 0 transformation takes objects from V and it sends them to 0, all of them. Okay, so the range of this 0 transformation is only object 0 from W, because everybody is sent to 0. Okay, everybody is sent to 0, so there's only one image. So the range is 0. Now kernel, or a null space of the transformation, are all the objects that the transformation sends to 0. While in this case, the transformation sends everybody to 0. So everybody from V is actually in the kernel. So kernel or null space of the transformation will be the space V, the domain. Because everybody is sent to 0 by this 0 transformation. If we have identity, so in this case you see we go from V to V, so that's why we call it operator. It's just a new term. You can still call it a transformation, it's fine. So identity transforms everybody into itself. So obviously the range is the entire V, because everybody is transformed to itself. So we cover everybody. So the range image here is everybody. Image of each person is itself, so range is V. Now kernel or null space is everybody who's sent to 0. Well, only one guy is sent to 0. 0 is sent to 0. So kernel in this case will be 0. Another example with a projection, let's say projection on x-axis. What does it do? Okay, I have a transformation from R2 to R2 for illustration purposes. So this one also, you can call it an operator. It's okay. Or you can just call it transformation, it's fine too. So what does this do? It takes an object, a vector from R2, and projects it on x-axis. So it basically just pulls it down. So it's every input is transformed into output of this sort, where the second component is 0 and the first component remains unchanged. Okay, so what's the range? So what's the set of images? Well, everybody is just pulled on x-axis. So the image is x-axis. Well, x-axis is span of vector 1, 0. You see it, x 0, you factor x, you get x of 1, 0. So set of all images is actually a linear space, span of vector 1, 0, so the x-axis. Okay, fine. Now question, what about the null space or the kernel? Well, that set of all vectors in R2 that are mapped to vector 0, 0. So the 0 object of R2 is vector 0, 0. So who are the guys who are projected on vector 0, 0? So everybody living on the y-axis. Okay, so those are people of the form 0, y. So if you factor y, obviously you get that kernel is span of vector 1, 0. Vector 0, 1. Okay, so everybody living on y-axis. So that's the kernel. So that's span of vector 0, 1. So that's the way we find it, the kernel and the range. For some transformations, it's easier than for others, obviously. So now, reminder of linear transformation. So it's a transformation that has all the nice properties as we saw before, but it also satisfies the two conditions of linearity. So linear transformations satisfy these two conditions of linearity. So T of the summation of U and V is summation of the images, and T of scalar multiple of an object from V is scalar multiple of the image. And as we said, in the case where V and W are finite dimensional spaces, and we are going to deal only with those spaces anyways, we can associate to the linear transformation a matrix, and we need to build that matrix, obviously. So what is important here is to remember the two conditions of linearity. Some examples of transformations that are not linear. Okay, so this one here, because of the sign, this transformation here, transforming people from R3 into real numbers using this formula here, and it's not linear because of the cosine. Obviously, function x squared is not linear. Also, function 1 plus x is not linear. It's a straight line, but it's not a linear transformation. Okay, because it doesn't satisfy any of the two conditions. So in order for a transformation to be linear, it must satisfy both of these linearity conditions. And the function 1 plus x doesn't satisfy any of them. So 1 plus x is not a linear transformation. We are mostly going to work with the linear transformations going from Rn to Rm, so finite dimensional spaces, but also only spaces of vectors, so columns of numbers. So this is just another name now for a linear transformation. It's going to be called matrix transformation also, and it's also linear. So every linear transformation from Rn to Rm is a matrix transformation, and every matrix transformation is a linear transformation. So for us, it's going to be the same. Whenever we deal with vectors, linear transformation or matrix transformation, that's the same thing. And we said when the domain and codomain are the same space, then we call it operator, but that's just a vocabulary, no need to suffer with that. The only thing here is that when we work with Rn and Rm, we can call it also matrix transformation, not only linear transformation. Both are the same, obviously, so it's just vocabulary actually. Again, the most important property of linear transformations is the linearity. So addition in the domain is also addition in the codomain, and the scalar multiplication in the domain is the scalar multiplication in codomain. So that's a very powerful property. As a consequence of this, we know that any linear transformation will map 0 from V onto 0 from W. So image of 0 will be 0 under each linear transformation. Obviously, it's not just a property of linear transformations. You can have, let's say, sine of x, sine of 0 is 0, but we know that sine is not linear. But what this says is that each linear transformation must map 0 to 0. That's a guarantee. It doesn't say that whoever maps 0 to 0 is linear. No. It just says if you're linear, you will map 0 to 0 for sure. And then image of the negative is the negative of the image. Also, one useful consequence is that if V is expressed as linear combination of V1, V2, Vn, then the image of V is also a linear combination of images of those vectors V1, V2, Vn. So this will be very useful as property. Some examples of linear transformations. So this one here transforms vectors from R2 into vectors from R2, so it can be called also a linear operator. And this one transforms vectors from R3 into vectors from R2 using this formula here. And then we have zero transformation identity. We saw last time that differential operator derivatives, that's also linear. Integral is also linear. Transpose of a matrix is linear. So linear transformations are not limited to only vectors, columns of numbers. They can take as argument matrices, functions, polynomials. For us, for now, we are going to focus on columns of numbers, but this is just to remind you that linear transformations are more than that. They can operate on different inputs, different types of inputs like matrices and polynomials and other functions. So our goal will be to find a representation matrix for our linear transformation. So again, we are dealing with linear transformations on finite dimensional linear spaces. So typically now we are going to deal with Rn and Rm. So those are finite dimensional linear spaces, and we can associate to each linear transformation a representation matrix. So that matrix, as we are going to see, will depend on the basis we choose for the linear spaces. So in this particular lecture, we are focusing on standard basis for V and standard basis for W. So we are going to call that representation matrix a standard matrix, and we are going to note it this way. So transformation and its standard matrix, so standard basis for the domain, standard basis for the codomain. So standard basis for inputs, standard basis for outputs. So that will be the subject of this video. Now in a different video, we are going to see how to build a representation matrix when the basis for V or W is not standard basis, when we take another basis. So that will be a different topic. But for now, all we want is to see how to build the standard matrix when V and W have standard bases. So procedure that helps us understand what's going on is presented here. So we have a linear transformation from Rn to Rm. So we are dealing with vectors here. And each linear transformation is defined by its action on the basis vectors. Here we are going to use standard basis for Rn and standard basis for Rm. So we apply actually T to standard basis. So more generally, if I take V from Rn, I can write it as a linear combination of basis vectors, obviously, from standard basis here. And these are like the coordinates in the standard basis. Now we remember that a vector in Rn is equal to its coordinates in the standard basis. So we can use that knowledge also. So in that case, if I have this linear combination here, if I apply T to the vector V, that means I'm applying T to this linear combination here. And now by linearity of the linear transformation, I can rewrite it this way. So what I see is that the linear transformation actually was applied to the basis vectors. So this now is actually a form that we recognize from matrix vector multiplication. So if we put image of first standard vector under T in the first column, image of the second standard basis vectors in the second column, etc., then we get a matrix here, and we have the coordinates of the vector V in the standard basis, so C1, C2, Cn. So T of V is actually just a matrix vector product. So that's how we actually figured out that we have image as a matrix vector product. And this matrix here is going to be called a standard matrix. So it is a matrix of images of standard basis vectors. So more formally, if we want to build the standard matrix, and we have standard basis for both domain and codomain, all we need to do is apply the linear transformation to the standard basis vectors and put the results in the columns. So that's expressed here. You take the standard basis, apply the linear transformation, you get the images, and then you put the images in successive columns, one after the other, and then you get your standard matrix. Simple as that. I keep this notation, it will be useful later on. So this just indicates that this is a representation matrix for linear transformation T relative to the standard basis for inputs, standard basis for outputs. For now, it looks like a an extra burden, but later on it will be extremely useful as notation. So that's how we build our standard matrix. Now, the good news is our matrix transformations or linear transformations from Rn to Rm, they have this matrix associated to them. So they are also called like matrix transformations. And so the action of the transformation is actually the same as multiplication by a matrix A. So the matrix is here, is the standard matrix. So now the good thing is, now it's going to be easy to find the range and kernel of the linear transformation. Range is just a column space of the matrix A, and kernel is the null space of the matrix A. So that's like straightforward computation. Here is an easy example to start. If I have a linear transformation that actually just multiplies by a fixed scalar every vector. So let's say I'm in R2 and the outputs are going to be in R2. So all I'm doing is multiplying by k, a scalar k, fixed number, each vector x. So how do I build the standard matrix? Well, it's simple. I need to apply the linear transformation to each standard basis vector. So I apply it to E1 to the vector 1, 0. So I get k times 1, 0. So it's k 0. And then I apply the linear transformation to the standard basis second vector 0, 1. So I get k times 0, 1. So I get here 0k. So all I do now to build the standard matrix is just put these vectors in the respective columns. So I get this diagonal matrix k0, 0k. So that's my standard matrix for this linear transformation. And if k is between 0 and 1, it's called contraction. And if it's bigger than 1, it's dilation. So it's shrinking and extending the vector. And when k is 1, it's obviously identity. So that's an example how we build the standard matrix. Just apply the linear transformation to each of the basis vectors of the standard basis and put the consecutive images into a matrix. That's all. So let's say here we are given a linear transformation from R2 to R2, and our goal is to build or construct the standard matrix relative to this linear transformation, and the linear transformation is given here. So this is what happens to the vector from R2 with components x and y. So we have some formulas that help build the components of the image. So we are using standard basis because we are here building standard matrix. We are using standard basis of R2. And as we said, we need to apply the linear transformation to each of the basis vectors. So we apply it to vector 1, 0, compute, we get the image 1, 1. We apply it to the vector 0, 1, and then we get the image negative 1, 2. So those input vectors get us the image. So the transformation applied to the input vector gives us the image, which is a vector 1, 1 and vector negative 1, 2. So all I need to do now is put each of these vectors into a column of a matrix, and that's my standard matrix that is associated to the linear transformation. Very simple, straightforward. So if I need to apply it, I take a vector from R2 and I apply the linear transformation to it. To get the result is just matrix vector product. Again, we remember that the coordinates of a vector in standard basis are equal to the vector. So the same thing as the vector. So all I do is just do the product matrix vector. So here in an example, if I want to apply a linear transformation T to vector 2 minus 4, I use the standard matrix associated with the linear transformation and multiplied by the coordinates of the vector 2, negative 4 in standard basis, which is the same as the vector, obviously. So I do the product and I get as the result the coordinates in standard basis of the image. Obviously, again, coordinates in the standard basis are equal to the vector itself. So the image of 2, -4 under the linear transformation is 6, -6. Another example, if I apply the linear transformation to a vector -1, 3, how I do it, I multiply simply the standard matrix by the coordinates of the vector in standard basis, which is the same as the vector, do the product, and I get the coordinates of the image in the standard basis, -4 and 5. Again, for a vector, its coordinates in standard basis are the same as the components of the vector. So it's the same thing. So the image under the linear transformation of the vector -1, 3 will be the vector -4, 5. It's very simple and straightforward. Here I have a linear transformation that transforms vectors from R2 into vectors of R3 using this rule here. So these are the formulas used to convert a vector with 2 components into a vector with 3 components using this linear transformation. So this is given in the problem. So all we need to do is just, again, apply the linear transformation to each of the basis vectors from the standard basis of R2. So our inputs are from R2. So we use the standard basis of R2. So T applied to the first standard basis vector gives an image, that is vector here, 0, -5, -7. And the image of the second standard basis vector under action of the linear transformation T is this image 1, 13, 16. So all I need to do now is put these images into a matrix, so into the columns of a matrix. And this matrix is the standard matrix associated with the linear transformation. Again, the first S is for standard basis, so standard basis for inputs, standard basis for outputs. So I just took the first image, put it in the first column, second image into the second column, and that's it. Similarly, in this example, we have a different linear transformation, but again from R2 to R3, and the same procedure, we apply the linear transformation to each basis vector, we get the image, and we put those images in consecutive columns of a matrix, and this is our standard matrix associated with the linear transformation. So this one, similarly, it goes from R2 to R2, so this can be also called a linear operator, if you wish, doesn't matter. So this is the rule how the vectors x1, x2 with the components x1, x2 is transformed into another vector in R2. So this is a linear transformation, and what we do, we apply the linear transformation to each standard basis vector. We get the image, we put the images into respective columns of a matrix, and that matrix is called standard matrix of the linear transformation T. It's very straightforward. Here, this one transforms vectors from R2 into vectors R3 into vectors R2. So it takes a vector with 3 components and it does something to it following this rule, and we get as an output vector with 2 components. So to build the standard matrix, this time I need to take standard basis for R3. So I apply this linear transformation to each of the standard basis vectors from R3. So I take first one, 1, 0, 0, I apply it, I get the image 1, 3, and this image goes into the first column of a standard matrix. Then I apply the linear transformation to the second basis vector in the standard basis, so the vector 0, 1, 0, and I get the image 2, 1, and this image goes into the second column of the standard matrix. And finally, I apply the linear transformation to the third standard basis vector, 0, 0, 1, and I get the image 0, negative 4, and this image goes into the third column of the standard matrix associated with the linear transformation T. So it's very straightforward. Apply the linear transformation to the basis vectors and put them in consecutive columns of a matrix. That's how you get your standard matrix. So here we have again a linear transformation, but this time it transforms vectors from R3 into vectors in R2, but it transforms into vector 0. So this is actually a 0 transformation. So again, I apply this transformation to each standard basis vector from R3, and I get, obviously, as a result, vector 0, 0. So I just put them into the columns, and this is my standard matrix associated with the linear transformation T. So it is a 0 transformation. By the way, we know by now that the range and the kernel of the linear transformation T are simply, range is the column space of a matrix, of the standard matrix, and the kernel of T is the same thing as the null space of the representation matrix. So that's very simple. So we go back actually to the column space and null space of a matrix. Very straightforward. In this example, the standard matrix for a linear transformation is given, but linear transformation in itself is not given. So we know that linear transformation is defined by its action on the basis vectors of the standard basis of R3 here. So these are the images of each standard basis vector under action of the linear transformation T. So we put each of these images into corresponding columns and we get the standard matrix representing the linear transformation. Straightforward. Even though we don't know exactly what is the linear transformation. Actually, we could recover it. It's just multiply this matrix by the vector x1, x2, x3, and you will get it. So now how do we use this? Well, what if we need to find the image of the vector 2, 3, negative 1 under the action of this linear transformation that is described by its standard matrix? So description of it is given by the standard matrix. Well, we are going to use linearity of the linear transformation, obviously. Since we know that vector 2, 3, negative 1 is a linear combination of the standard basis vectors, now we apply T to that vector, and by linearity of the linear transformation T, so we have T applied to the linear combination, which is equal to the linear combination of images, and we are given already the image of the first standard basis vector, and we are also given the images of the second and third. They are given here, so these images are given already, so I just use them. So it's 2 times the first image of the first vector from the standard basis from R3 plus 3 times the image of the second minus image of the third, so I add them and I finish. So that's the image of T, image of the vector 2, 3, negative 1 under the action of linear transformation T. So the image is 8, 4, 7. Another way of computing the same thing is just multiplying the standard matrix by the coordinates of the vector in standard basis, which are the same as the vector, obviously. So you just do the matrix vector product and you get the coordinates in standard basis of the result, which are the same as the result itself. So the image of 2, 3, negative 1 under the action of linear transformation T is just the product of the standard matrix by the vector itself, and you get the image. Simple, simple, simple. Another example where we actually try to find also range and kernel of a linear transformation. We said already that range is the column space of the representation matrix A, and the kernel is the null space of the representation matrix. So here I have a linear transformation that is defined by its standard matrix. Obviously I can find what is the linear transformation itself. I just multiply the standard matrix by the generic vector from R2, because this one goes from R2 to R3. So x1, x2, just do the product, and this is what I get. So this is my linear transformation, transforming vectors from R2 into vectors from R3. As we said, the range of the linear transformation will be equal to the column space of the representation matrix. Another way to see it is you just take the expression of the transformation and you factor x1 and x2, and you see obviously that the images are linear combinations of these two vectors. So that means then the range of the transformation is the column space of the standard matrix, or in other words, it's the span of these two vectors here. So range is span of these two vectors, which are actually the columns of the representation matrix in standard basis. So that's very straightforward. So if I need to find image of the vector 2, -1 under action of the linear transformation T, all I need to do is just do the matrix vector product and I get the image. So this is standard matrix times the coordinates in standard basis, which are the same as the vector, and I get the output in standard basis of R3, which is the same as the vector itself. So it's very straightforward. There's nothing special here. A very curious question. We need to find a vector x in R2 whose image under the linear transformation T is vector B, and vector B is given here. So that means we need to find x such that T of x is equal to B. So we need to solve this equation for x. But we remember that action of T on vectors in R2 is expressed by the matrix vector product, where matrix A is actually a standard matrix of the linear transformation, and we get already that one. So we need to actually solve the linear system Ax equal B. I use Gauss-Jordan to solve it, and we find a unique solution, 1.5 and -0.5. So A is the standard matrix for the linear transformation T. So we just apply the Gauss-Jordan to this system. And we found x. So this is x such that T of x is equal to B, given here. T is represented by its standard matrix. So T applied to x is actually Ax. It's the same thing. And vector B is given here. Okay, so we found the input x such that T of x is equal to the output B. So that was interesting. Another question, is there more than one input x whose image under T is equal to B? Well, no, because we just solved it. We solved the linear system and we found that there's a unique solution, 1.5 and -0.5. So in this particular case, for this particular B, there's exactly one input x whose image is this particular B. Okay. It doesn't mean it's going to be always, but it just means that for this one, it was the case. So another note regarding the range, if we try to find an x whose image under T is some vector B, that's the same as trying to find the solution for the linear system Ax equal B. We saw that already. Which means that's the same as asking the question, is the vector B a linear combination of these two columns here? So another way of asking the same question is is B in the span of these two vectors? Or is B in the range of the linear transformation? Or is B in the column space of the representation matrix A? So we have like thousands of ways to ask the same question. Another question with the same transformation. We need to see if the vector C given here belongs to the range of the linear transformation. So range of the linear transformation is the same as the column space of the representation matrix in standard basis. So it's the same as the column space of the standard matrix A that we found. So we need to see if the linear system Ax equals C has a solution, or does C belong to the column A? So that's the same question. So we need to solve the system Ax equals C. How? Using Gauss-Jordan, obviously. We compute and we found that there is a contradiction in the system, which means this system does not have a solution, which means that the vector C is not a linear combination of the vectors given here, which means vector C does not belong to the span of these two vectors, which means that vector C does not belong to the range of the linear transformation T, or vector C does not belong to the column space of the matrix A. So it's all the same thing. Therefore, C does not belong to the range of the linear transformation T, because the system here is inconsistent. So we have several ways to formulate the same question in this case. Another question is, how can I find a kernel of the linear transformation? Well, kernel, or the null space of the linear transformation, is equal to the null space of the representation matrix, standard representation matrix. So all I need to do is find the null space of the matrix, which means I need to find all the solutions for the homogeneous system Ax equals 0. Okay, just do the job. And it turns out that we have one unique solution, vector 0, 0. Wow. So kernel of the linear transformation, which is equal to the null space of the matrix A, representation matrix here, is actually only vector 0, 0. So this is just a reminder that a kernel of a matrix transformation or linear transformation T is equal to the null space of the standard matrix. Finally, we can compose transformations, also linear transformations, obviously. So if I have a linear transformation T1 going from U to V, so linear space U to linear space V, and then linear transformation T2 going from linear space V to some linear space W, I can compose them in a certain way. So I have a composition here. So this is a linear transformation also. So composition of two linear transformations is a linear transformation. So graphic illustration here of what's going on. We take a vector from U and then we apply T1 and we get an image, and then to the image we apply T2, so we get the image in the W. So you take one bus and then you take another bus. And the composition is this transformation here that does the job immediately. No intermediate steps, it just does everything in once. So be careful, here we apply first T1 to the input from U, and then to the result, so we apply T1 to the input U, and then to the result we apply T2. So U, we apply T1 to U, and then to this result we apply T2. Okay, so that's what is described here. So what we need is to find what is this composed linear transformation. So here is an example. We have, in this case, two linear operators from R2 to R2, both of them. And the first one, T1, transforms vectors from R2 in this way to get another vector from R2, and T2 has a different formula for each component. So our goal first is to find the standard matrix for each of these linear transformations. So that's easy because we apply each transformation to the standard basis vectors from R2, and we get the image, and then we put these consecutive images in consecutive columns, and this is our standard matrix associated with the linear transformation T1. Similarly for T2, we get the images and we put them in consecutive columns, and we get the standard matrix associated with the linear transformation T2. Now we want to find the standard matrix for the composed linear transformation. So we are composing T1 and T2. So we are first applying T1 to the input, like here, and then the result, T1x, to that result we apply the transformation T2. So the order is very important. So we remember T1 of x is actually just the product of the standard matrix associated with T1 with the coordinates, standard coordinates of x. And for T2, similarly, applied to z in this case, we multiply the standard matrix associated with T2 with the coordinates of vector z in standard basis. So if we follow this logic here, we apply T1 to x, so we apply T1 to x, so we multiply these two. To the result, we apply T2. So T1x goes here instead of z. So that's what happened. So that's why we have the standard matrix associated with T2 times standard matrix associated with T1 times x. So it follows this order here. So it's not complicated, nothing changes. Just put the standard matrix associated with T2 times standard matrix associated with T1 times the coordinates of x, puff. Same order, nothing changes. So if I do the product of these two matrices, I'll get the matrix here. So this is my standard matrix for the composed linear transformation. So that's, if you multiply these two matrices, you'll get the matrix here, 3, 6, -2, -10. So this is a standard representation matrix for the composed linear transformation. So composition was T2 composed T1. Okay, and you see what happened is just we follow the order of these representation matrices. They follow the order of the linear transformations. So nothing special here. So standard matrix for the composition is product of standard matrices of each particular linear transformations. So not big deal, we just do the product of matrices, we get this representation matrix for the composition T2 circle T1. So if I want to express this composed linear transformation in a similar way as the definition of T1 and T2, so I have the standard matrix here, and all I do is just multiply it by the standard basis, standard coordinates of a vector in R2, which is the same as the coordinates of the vector itself. So I get this vector here. So I'll just rewrite it differently a little bit, but it's the same. First component is this guy and the second component is this guy. So the linear transformation, that is the composition of T2 and T1, is expressed this way. So that's it. We had the standard matrix and we multiplied by x1, x2, and we got the description of the new composed linear transformation T2 circle T1. So the order is preserved, nothing special. Similarly, if I want to find a standard matrix for the composed linear transformation T1 circle T2, so it's different from the previous one, In this case, we apply T2 to the input from R2, so T2x, and then to this result, we apply T1. So you see the order, T2 is first, and then to the result, we apply T1. So that's what it means. T2 is applied first, and then to the result, we apply T1. And again, how do I do this? Well, I have a standard matrix representing T2, and I multiply by the standard coordinates of x from R2, and for T1 and Z is the same thing. So here Z will be T2x, we'll bring it here, so that's what you get. You get this matrix here, and then the matrix from T2x, you'll get this guy and x. So the order is actually preserved, you see. T1 circle T2, what you do is you multiply the standard matrix associated with T1 times standard matrix associated with T2 times coordinates of x, path. So you do the product of these two matrices, and you'll get the standard matrix for the composition. So the standard matrix, once I do the product, the standard matrix for the composition T1 circle T2 is this. So that's simple. Now if I want to get more specific, so this is the same details of the process, just product of these two matrices in the correct order, you see, T1, T1, T2, T2. So standard matrices for T1 times standard matrix for T2, boom, do the product, you get the standard matrix for the composition T1 circle T2. If I want to get more specific here, I can use this standard matrix and then just multiply it by the standard coordinates of a vector x1, x2, which is the same as vector x1, x2, by the way, because it's standard basis for R2. And all I do is just write the components here. So this is expressed in a similar way as the linear transformations T1 and T2 at the beginning. So this is just to mirror the same notation. Obviously, you see that the representation matrix for T1 circle T2 was different from the representation matrix for T2 circle T1. We know that order of multiplication matters for matrices, so we don't even expect them to be similar. So all this is quite straightforward procedure. You can solve a lot of problems here just to practice finding the standard basis, the image of the standard basis vectors, build the standard matrix, find the image of certain vectors and stuff like that, find the standard matrix for composition. So all the notions that we have seen are covered in these problems here in the white cover book. The exercises from the yellow cover book are not really interesting for section 4.9, but you can only focus on the white cover book, these exercises here, and you'll have a lot of fun. It's straightforward and quite easy.